finish this off by talking about Joule's law, which is the equation for electrical power. We're going to talk about the definition of power, in case you haven't covered power before at all. And we're going to talk about how to combine the definition for power, Joule's law for power, and Ohm's law all together to solve puzzles in physics. So let's go. Let's do this. So we start off at the top in our packet. This is page 20. And this is number 28 that we're going to begin with. And I've written Joule's law at the top here in green. It is PIV, P equals I times V. And I just say PIV to remember it, just like I say VER for Ohm's law. And then I say PET for the definition of power. And we'll see that in just a minute. Now, we're getting all the answers here. So our job is to actually show how to get the answers. And let's take a look at number 29 together. A lamp operates at 10 volts. There's our voltage. I've written a V. And draws a current, which is an I, a current of 0.5 ampere for 60 seconds. And so that 60 seconds is giving us a change in time. And then they're saying, hey, what power, capital P, is developed by the lamp? And so the answer is 5 watts. How do we get there? We start with our equation, Joule's law, P equals I times V. And then notice that we're not going to need that time. That was an extra piece of information. We can still get there with just the I and just the V. We're going to just put in 0.5 amps for I, and we're going to put in the 10 volts for our voltage, and we're going to get our 5 watts of power. And the unit for power is the watt, as we saw in the previous video, named after James Watt. So we have two Jameses here. We have James Joule for the unit of energy and James Watt for the unit of power. Okay, so that's a basic one. Let's get a little bit more in depth. Let's jump over to, and so just here's a little tip for number 30. You're still going to use PIV, and then go to 31. In 31, you see that you have a V, an R, and a P. And so PIV isn't going to work directly because you're missing the I, and you have an R in place of it. So let's take a look at a skill we're going to find in number 32 that will help you go back to 31 and solve it on your own. So in number 32, we're going to have to combine Joule's law and Ohm's law. And so I've written Joule's law there on the left and Ohm's law there on the right. And I'm kind of color coding these so you can see what's going to happen. The question is, which is a unit of electrical power? And so we know the SI unit for electrical power is the watt, capital W. The unit we use for power here in America is horsepower, like with our cars. But so which of these, a volt over an ampere or an ampere squared divided by an ohm, or an ampere divided by ohms, or a volt squared divided by ohms, would be equal to a unit for power? Now, actually, secretly, a volt squared divided by ohms is the answer, and it is equal to a watt. If you have 1 square volt divided by 1 ohm, that is equal to a watt of power. How do we prove that, though? Because that's what we have to do. So let's take a look. We have Joule's law, PIV. Now, if I put in the units instead of the quantities, the quantity being power, current I, voltage V, but the units being watts, amperes, or amps for short, and volts. So we could see if one of the choices was an ampere times a volt, then that would be the answer and we'd be done. But they're not going to be that nice to us. They're actually going to have a volt divided by an ampere up here in A, and that's not going to be an ampere times a volt. So that's not going to work. So we can cross off A. We know that's not going to work out. Over here in Ohm's law, we're going to have to resort to Ohm's law and see if we can work this out. We need to get ohms into our equation for power somehow. And so ohms are found as a unit for resistance, and Ohm's law has resistance in there as that blue R. And so what I'm going to do is I'm going to play around with Ohm's law to try and put in the R into the Joule's law equation for power. And what I see here in my answer is I'm actually going to need volts, so I'm going to need V's, and I'm going to need ohms, so I'm going to need R's. What I don't need are amps. Amps are not in the answer. So I'm going to get rid of I in PIV. And to get rid of I in PIV, I need to substitute other letters in its place. This is a basic skill we need to have when we're working with our physics. We do this pretty often. So let's see how to substitute things here. So the first thing I want to do is get Ohm's law solved for I, and then I can know what I is equal to in terms of V over R. And so let's do that. I'm going to get rid of R on the right side, and so I have I by itself. So I'm going to divide both sides in ohms by R. Let's keep the colors. Let's keep the colors going here. So there's R. Okay. And so then R's cancel on the right, and I get I by itself, and I see that I is equal to V over R. Now, if I write that from left to right, like we like to read our English sentences, we can read our math the same way. So then I would equal V divided by R. So there's my purple V, and there's my blue R. So now I know that I is equal to V divided by R. So I can kind of put those in parentheses and put them in place of I over here in Joule's law. And so I can put in my divider line and my V divided by R. And then I still have my V from PIV right there, and then that would equal power. So power is equal to V over R times V. Now to simplify that a bit, I could put another equal sign here and just do a chain of equal signs to simplify this down. So that'd be V times V, that'd be V squared. So that'd be V squared divided by R, and so put R underneath there. And now let's do what we did before up here. Let's do that to this. Let's put in the units in the place of the quantities. Right now I have the quantities. So what I would see in place of these is that I'm looking at voltages for V. Now that's going to be the same letter, but slightly different meaning. So I'm putting in parentheses to show that I'm putting in units now, not quantities. And then ohms for resistance, and we have this wonderful little pun in physics where we use a Greek omega. It's a Greek omega for ohms, because we couldn't use an O for ohms. It's named after George Ohm, a German physicist. But we couldn't use an O for his last name because it looks too much like a zero. So we have omegas, which is like a pun, omega for ohms. Now we're looking for volts squared divided by ohms, and that's actually the exact answer. So that works out for us. So that's what you do. This is a pretty advanced level of thinking and working with your equations. So if it doesn't seem natural to you at first, don't feel stupid. You're just developing in this area. This is literal equations. We saw this before with Ohm's law, but now we're going to combine ohms with joules. As the resistance of a constant voltage circuit is increased, the power developed in the circuit does what? So we are trying to connect resistance R with a voltage V, and it's going to stay constant, and then we're going to be finding a power P, and we're seeing what happens to the power. And so we don't have like ohms and joules, like in their pure sense, they don't have VRP. So, but we did just actually develop an equation up above. You see how up here we have V squared over R equals P? And so I could just steal that and use that down here, or I could do a chain of thought. And let me do the chain of thought with you very quickly. I already have it written here just to kind of show you. So if the voltage is constant, we'll lock that in a box, draw a square around it. It can't change. But then what happens if the resistance increases? So there's an up arrow for that. Well, if the resistance gets bigger, but the voltage has to stay the same, then the current would have to get smaller. And so then the current gets smaller. Now carry that idea over into PIV. Now the current is getting smaller and the voltage is staying the same. So then what would have to happen to the product of those, the product being the power would have to get smaller. And you can do an example of numbers, and if you'd like to see how to do an example of numbers, then you can check that out in our last video again. And so then let's take a look at number 34. Number 34, we get to see the definition of power. And power is defined as the rate at which you can change the energy of something. And changing the energy of something is called doing work on that thing. So power is the rate at which work is done. And so if we write that in terms of energy, we'd write delta E here, changing the energy of something. And so you can write it in math language. Power is, equal sign is, the change in energy per or over the change in time, over a change in time. And so we have this question where it's asking us, hey, if we're going to take the power and we're going to double it, so we're going to multiply the power by 2, then what happens to the energy used in 1 second? And so the 1 second is going to be constant, so we're going to kind of say that, all right, we're going to lock our change in time in a box, just like we did with voltage earlier. So it's not going to change. But then the power is going to go up. So the power, we're going to double the power. I'll draw that bigger to show that we're going to have more power. So then if the change in time has to be the same amount, 1 second, then what would have to happen to keep this equal sign true? Well, we'd have to see more energy changed. We'd get a bigger number here. In fact, if we had twice the amount of power, we'd have twice the amount of energy change. And so it's almost like, if you want to think about it another way, whatever you do to one side of an equation, you have to do the same thing to the other side of the equation. I mean, that's one of the most basic rules in Algebra 1, So if we were to do that, let's just do okay, so here's power equals change in energy over change in time. And then multiply this side by 2. Okay, so there's 2 times P. We doubled that. Well, now this wouldn't be equal anymore unless we do the same thing to the other side and then multiply it by 2 as well. And so we'll put a 2 here to show I'm going to multiply that by 2. They said the time is 1 second, so the time is not going to be changing. So what changes is the energy gets multiplied by 2. The change in energy gets multiplied by 2. And that would be doubling it. So there's an idea of working with equations without having specific numbers.